Hello everyone, the problem that we'll look at today is an old friend of ours from December contest of last year, the problem 3, 2D conveyor belt. So you can pause the video first and read the problem yourself, and since the problem statement is quite straightforward and is very long, I'm just not going to explain it and not just have you read it. Okay, so I assume you already read the problem. Here are some examples, and a very basic summary is you're building grids on a conveyor belt where the letters represent where it goes, and now after building I of the n by n cells in this grid of conveyor belt, you're trying to determine the minimum number of unusable cells, meaning a cell that will not allow an object to exit. You're trying to find the minimum number of unusable cells if you build the remaining cells on this conveyor belt optimally. So you can pause the video once again and try to figure this out yourself. Okay, so I assume you already gave this a try. First of all, notice that since there can be at most 2 times 10 to the 5th power, a brute force solution will exceed the time by quite a lot. And after a while, we notice that considering this in the forward order is actually quite difficult because every single day you add a constraint, and adding a constraint affects a lot of cells because you need to know which cells depend on this one in order to be usable. And after changing it, you have to change the usability of all these cells. And that's just quite difficult to do. So usually in situations like this, the trick that we use is to consider the queries in reverse order. So basically in this one, it's at first every single cell is built and then you remove them one by one, which will make it a lot easier. So let's say, first of all, let's draw this grid out. We have a 3x3 grid with 5 queries. So obviously in this situation, the number of cells that are unusable after we have constructed all the entire 3x3 grid, since we're considering it backwards, is 3 of them, right? Because notice how these 2 cells will just repeat indefinitely, and then this one leads to this cell, which will also lead to whatever object placed on this cell to repeat in this cycle indefinitely. And if we start removing them one by one, we'll see the number of unusable cells start decreasing. And it's actually way more calculatable than if we just add them one by one. Because think about it. If we remove this one, then all we have to do basically is to see if any of the other 3 directions that it did not lead to is now usable. And if it is, we just got to update the usability of the singular cell and every other cell that goes onto this cell. And we don't have to check the cells that are already free, just those that are not free. And notice how each cell will only become usable once. So each cell will only be enumerated once, guaranteeing us the time complexity. So specifically for this cell, we know that it used to feed into this one, the cell 1, 1. However, now that it's freed, we can make it feed into any of the other adjacent cells. And notice how this cell on the left, which I didn't draw, this cell on the right, and this cell below that are all usable. And since all of them are usable, this cell becomes usable, right? And now we just have to check every cell that leads into it and see if it's usable. And since there's none right now, let's just say that we had an earlier constraint of doing this. At first, this cell was unusable as well because it leads into this, and this one leads into this infinite cycle. However, now that this cell is usable because the one on the left is usable, we just have to start a reverse DFS process that goes to this cell, update it as usable, and then go to any other cell that also leads into this cell. See this one, and maybe that's usable now, and this one is also usable. And notice how if a cell does not become usable in this turn, we will not reach it. So the time complexity of this solution is guaranteed to have a total of n squared, which is 10 to the 6th power, and that is acceptable. So here is my... Okay, so for each cell that's outside of the grid, obviously, we count it as usable. So we count all the outside cells and we add them to the initial answer, because we know this answer is actually going to be the last answer since we're processing them backwards, but we have already added all the constraints. So this is the answer for the grid after all constraints, which is going to be the last one that we output. And we also do a pre-DFS process where we basically start from any border cell that's originally usable, of course, and every single cell that can be used, that can be reached through a reverse DFS process from any border cell is also usable at the beginning. And then we start processing the queries backwards. Each time we, first of all, obviously change this cell to anything, so it's 0 now. And if this cell was usable at first, well, then we don't have to do anything. However, if it turns into usable from unusable, then okay. For example, if it's at first it was unusable, we don't know whether it turns into usable or stay as unusable. So we had to go through all 4 of the adjacent cells and see if any of them are usable. And if any of them works, then this one must work. And now we do a DFS process if any of the sites on all the site cells, updating them as usable now, if they weren't usable. So let's go to the DFS. Oh, I only wrote one DFS function. Okay, that's funny. All right, so we have basically the same process that we did for the pre-process as well. So very convenient. We just go to each cell, and if we can reach this one, we just mark it as usable. The exact same DFS process. And it is quite simple and straightforward because you just, find the opposite of each cell, and then you go reverse order. If you can reach that cell, you go to that cell. If that cell was already used, you skip it. If that cell wasn't used, you update it as used, and then you go to that cell, DFS and X and Y, sending for the new X and the new Y. And obviously, each time you have to update the answer, then you just output the answer in the forward order again. However, notice how we counted the usable cells in this one, so it's just n times n, which is the total number of cells minus the number of usable cells, giving us the number of unusable cells. Okay, so that is the kind of long problem review of the USACO 2024 December contest silver problem 3 of 2D conveyor belt. I hope this video helped, and thank you for watching. I'll see you tomorrow. Okay, that was it for the problem review of this video. That was a pretty fun problem from December, and one of the biggest reasons why I could not get to gold back in last December, and that is because I actually did not start from every single border cell into inner cell. Rather, I DFS from every single inner cell, and that will result in an implementational mistake, basically. But it does not matter. Okay, so from the grinding report today, I did not really grind at all. I did one problem from a class that I'm taking right now, and it's a really simple binary lifting problem, and even simpler considering that the unit is all about binary lifting. Yeah, we can't really translate this into English because it's just a screenshot, but basically what you're given is simple binary lifting. I'm not even going to explain it, and I did that. Took literally less than 30 minutes and slacked off the other 23 hours and 30 minutes. Good enough, whatever. There's always tomorrow.